Homework pressure? No more. At Spring Library, we explain every topic in simple way. Join the learning family and score high every day.
Question 9 in our book states that a 2-kilogram tumor is being irradiated by a radioactive source. The tumor receives an absorbed dose of 12 gray in a time of 850 seconds. Each disintegration of the radioactive source produces a particle that enters the tumor and delivers an energy of 0.40 MeV. What is the activity? Delta N over delta T. Here I just put N over T. As we observed in chapter 31, section 6. So what is the activity of the radiation source? So our goal for this problem is to solve our givens for this expression of activity, N over T, or delta N over delta T, whichever you prefer. So we're told a couple of things here. Dose, time, mass, and energy per disintegration, which I just referred to as N number of events, disintegrations, particles, whichever you use is kind of a catch-all variable here. So in this scenario, if I want an expression for N over T, the number of disintegrations per time frame, based on what I'm given, I can sort of build a relationship so my variables are in the same locations. So first of all, very easily, I need time in my denominator. So it's very easy. I need to divide by T. I need number of events in my numerator. The only term that I have that gives me number of events is Q over N, but N is Q over N, so that means my Q over N must be on my denominator as well. Q over N. And so now I'm left with an energy on the denominator. So that means my numerator must have some sort of energy term. But I can get that based on what I have for energy and mass. So my energy, total energy, I'll say, there's Q, is on my denominator, which I'm going to replace that actually. My total energy was found to be, if we just look at the relationship, energy over mass equals dose. Therefore, this is my total energy. I will put that. So total energy is simply mass times dose. So you can put that under numerator here, M times D. So this expression gives us units of N over T, the radioactivity, that we want to find, and we can just plug it in and we'll convert units as we need. So the mass that we're experiencing, 2.0 kilogram, multiplied by a dose of 12 gray. Note that our numerator, as of right now, provides in joules. Actually, I have to delete that because I need space. But just note, gray joule per kilogram times kilogram is just joules. In our denominator, the exposure time is 850 seconds, multiplied by our ratio Q over N, 0.40 MeV over N. So as a good thing we noticed that in our numerator we do have joules, in our denominator we have MeV, so we need to convert one to another. So it doesn't matter if you want to get rid of MeV or get rid of joules. I'll get rid of my joules term. So I know to convert joules to MeV, I use 1.6 times 10 to the negative 13. There are that many joules per 1 MeV. And let me just check my units to see if I need to do anything else. Well, gray times kilogram, again, is just joules. So these two terms cancel out joules. Our MeVs cancel out. And we are left with seconds in our denominator and 1 over number of events in our denominator, which is put the N in our numerator. And so we are all satisfied with our units. And by multiplying this term out, we would find that our decays per second is 4.4 times 10 to the 11. You can put N per second if you like, decays per second, or often you'll just find it represented as inverse seconds, where N is kind of an assumed value. So either of these are correct, and to two significant figures, this is extra correct. So there you go.